Refraction is defined as the bending of EMR, and it's due to what? When does EMR bend? When does it change direction? When there's a change in the medium, and therefore a change in the speed. So when the speed of the wave, in this case EMR, changes as a result of going from one medium to the other, then the direction will also change as well as the wavelength changing. If the index of refraction, which remember is a measure of how much light bends, it's the ratio of the speed of light in a vacuum to the speed of light in the medium. If the index of refraction increases, then what happens to the speed? N goes up, V goes down. Good. If V goes down, then lambda goes down. If V and lambda go down, then theta will go down. So if N goes up, the index of refraction increases, you're going to get V and lambda and theta all decreasing. Good. Take a look at the diagram up here. If we have EMR, visible light, let's say, going from air to glass. Air is an index of refraction of 1.00. There's different types of glass, but on average they have an index of refraction of about 1.00. Keep in mind that that would vary by color as well, but not dramatically. If we have EMR going from air to glass, that is a low index of refraction to high index of refraction. That means the light will speed up or slow down? Slow down, and if it slows down, then theta will go down as well. It'll get smaller. So theta 1 is going to be bigger than theta 2. And it doesn't matter how big we make the value of theta 1. Here theta 1 is really big, right? 80 degrees-ish. What's going to happen here? Well, it's still going to slow down when it goes into the second medium. And if it slows down when it goes into the second medium, theta 2 will be bigger than it was before, but it's going to be smaller than theta 1. Theta 2 will always be smaller than theta 1, and you're not going to get reflection under any circumstances here. It's going to always refract. But if we go the other way around, if we go from glass to air, from a high index of refraction to a low index of refraction, N goes down, then V will go up. And if V goes up, theta will go up. That means that theta 2 is now bigger than theta 1. We say that it bends away from the normal line, right? This would be bending toward the normal line. This would be bending away from the normal line, or theta 2 being bigger than theta 1. If we increase the angle of incidence to a big, big value like, say, 80 degrees like we did in the last case, then sometimes what we might get is reflection. We call that total internal reflection. It's the light skipping off the boundary as opposed to refracting into the new medium. Now, there is an angle, a special angle, at which reflection begins to occur. What do we call that? The critical angle, right. And the critical angle that we'll draw in red here is the angle of incidence right here, theta 1, the value of theta 1, where the ray of light just kind of skips along the boundary. If you decrease the value of theta 1 below the critical angle, it's going to refract just like the blue line. If you increase it above the critical angle, then it's going to reflect just like the green line. Now, this is where we left off on Friday, sorry. How do we find the critical angle? How do we find the angle at which reflection will begin to occur? Yep. Yeah. Yes. So we're going to use Snell's law. And Snell's law is sine theta 1 over sine theta 2 equals, well, it equals, right, V1 over V2, and it equals lambda 1 over lambda 2, and it equals N2 over N1. And we could use any other part, V1, V2, lambda 1, lambda 2, N2 over N1. But almost always, just because of what we're given in these questions, it's almost always going to be the last part, N2 over N1. Keep in mind, if you were given the values of the speeds instead of the indices of refraction, well, then you could use those in order to determine the critical angle. But usually it's going to be like, in fact, I can't remember a case in my time teaching physics 30 of 23 years where we've had to find the critical angle given speeds as opposed to given index of refraction. I can't remember a single time. but it's absolutely possible, right? It's just would be very rare that you'd be asked that. Okay? If you are, then no big deal. Okay, sine theta 1 over sine theta 2 equals n2 over n1. Nick just told me a second ago that if I want to find the critical angle, then I'm going to set theta 2 equal to what? What was it, Nick? 90 degrees. Because at the point where the light skips along the boundary, we could say that the index of refraction, the angle of refraction as measured from the normal line, that imaginary dotted line that's drawn at 90 degrees to the boundary, is 90 degrees. Now, if you don't remember this, take out your calculator and type it in. Sine 90. What's the value of sine 90? 1. 1. So it always becomes sine theta c over 1 equals n2 over 1, n1. Theta c is therefore the inverse sine of n2 over n1. Now, there's a little bit of good news with this. We're going n2 over n1. So the value of n2 in these critical angle problems, not regular Snell's law problems, but critical angle problems, n2 will always be smaller than n1. So you're always going to get a decimal number inside those brackets. If you get mixed up and go n1 over n2 here, again, this doesn't work with regular Snell's law, but with critical angle problems it does. If you get mixed up with between n1 and n2, and you type this into your calculator is going to give you an error every time. So if you mix up the indices of refraction here, you'll know you made a mistake. Okay, and typically the mistake that you've made is just that you flipped over the indices of refraction. So fix it and do it again. All right? All right. Now, this is just a summary of what we've just said, right? Total internal reflection, or sometimes we abbreviate it TIR, total internal reflection, is when light reflects off of a boundary rather than refracting. And it can only happen, this is really, really important, it can only happen when you go from a high index of refraction to a low index of refraction. And of course, only if the angle of incidence is big enough. Only if the angle of incidence is big enough. In other words, if theta 1 is greater than or equal to theta c. Theta c, the critical angle, is the angle at which total internal reflection begins to occur. Anything below that, it refracts. Anything above that, it reflects. Now, before we do an example, before we do a calculation example, let's do a couple application examples here. This is a pond. Okay, and let's say we got a person standing at the edge of the pond here. Person's looking in the pond, and the person sees this fish, this bottom feeder fish that's at the bottom of this pond. He's happy because he hasn't been caught yet. Now, there's lots of sunlight coming into this pond from up above the surface, right? And there's millions of rays of light that actually strike the fish and reflect off of this fish in every which direction, essentially an infinite number almost of directions. We're going to pick one ray of light that's reflecting off of this fish. We're going to pick this one. This ray of light reflects off of the fish in this direction. We know there's a million others, but let's just focus on this one right now. Now, that ray of light bouncing off of the fish strikes the boundary between the water and the air. Keep in mind the index of refraction of water is about 1.33, and the index of refraction of air is about 1.00. So as this light strikes the boundary between the water and the air, as it goes from high index to low index, what's going to happen to the speed of the light? It's going to increase. It's going to speed up, right? If v goes up, then theta will go up, right? So as measured from the normal line, theta 2 will be bigger than theta 1, right? This is theta 1, okay, this is theta 2. Theta 2 is going to be bigger than theta 1. Still refracts, okay, but the theta 2 is going to be bigger. This ray of light I chose because it's this ray of light that actually refracts into the eyes of the person standing at the edge of the pond, and therefore it's this ray of light that allows the person to see that part of the fish. Does that make sense? Now, understand though that our brains have become smart enough to realize certain things, but not really detect certain things properly. We just think about it and figure, oh yeah, my brain's playing tricks on me. When the person sees this fish, the person doesn't see the fish where they are. The person sees the fish back here. Because our brains intuitively interpret that ray of light as always having traveled in a straight line. So, to the person standing at the edge of the pond, it looks like the fish is back here. Does that make sense? Right? We see that pencil in the water and the pencil appears bent. We see the pencil in the water somewhere other than where it really is. We see the fish in the water somewhere other than it really is. So the fish appears behind where it really is, and it appears not as deep as it really is. Make sense? This is not total internal reflection. Not yet. Okay, but just wait. Okay, we're getting there. Question?
So is it just like it's light, so light hits it pretty much generally, or does it have to be like a specific angle?
No, the light hits it generally. Like when the light hits it, okay, this fish, you're going to have almost an infinite number of rays of light coming off. So in other words, the light's going to come off at effectively every angle, including this angle. We've just drawn one of the million rays of light. All right, let's change it up a little bit here now. Let's say that this person decided to back up. So this person is now back here. This ray of light that reflected off of the fish is still reflecting off of the fish, but where does that ray of light go now? Right over the person's head. Does that person see the fish from that ray of light? No, so this disappears, right? Person doesn't see that. Well, in order for the person to see the fish now, there is like a million rays of light, right? Maybe it's a different ray of light that would refract and cause the person to see the fish now. Let's pick a different color here. Like, understand that when I pick a different color here, we're not changing the color of the light. I'm just picking a different color to draw this so that you understand the difference between the two rays here, okay? So this one is reflecting off of the fish like this. Okay, maybe that one will refract into the person's eyes now. We have a problem though, potentially at least. This ray of light that might refract into the person's eyes is now at a bigger theta I, or theta 1, than the yellow one was. What if this purple ray of light hits the boundary between the water and the air at an angle above the critical angle? Could it be a critical angle here? Yeah, we're going from high to low index. There could be a critical angle. What if it's above the critical angle? Then what happens to it? It reflects down like this. So what does this person see? Nothing. Have you ever noticed that? Like you go golfing, you hit your golf ball in the water, and you go right up close to the pond, and you see the golf ball there? Although when you go to stick your golf ball retriever in the water, the golf ball's not really where it appears to be, right? The fish isn't where it appears to be. When you back up from the pond, at some point all of a sudden the golf ball disappears. Well, it disappears because all the light reflecting off of it reflects off of the boundary between the water and the air. It didn't when you were close because those rays of light that were going into your eyes weren't reflected because the angle of incidence was smaller. Now, you also don't see the bottom of the pond when you're backed up from it, right? Because the bottom of the pond behaves just like the golf ball or the fish. The rays of light that would be required to be refracting into your eyes are reflecting off of the boundary between the water and the air. Does that make sense? Okay, this is a perfect example of total internal reflection. By the way, where would you need to be in order to see the fish using this purple ray? Where would you need to be? Sorry? Well, if you're closer to the lake, you could see the fish, but it wouldn't be with this purple ray. Where would you need to be in order to see the fish from this purple ray? Underwater. You'd have to be right here, laying down on the bottom of the pond or the side of the pond. Now, this is kind of an exercise in physics, theoretical, not necessarily practical, because you're probably not going to be laying on the bottom of the pond looking at this fish. But let's say you were. Where would you perceive the fish to be? Where? No. The fish would appear to be up here. Because our brain intuitively perceives that ray of light to have always traveled in a straight line. Now, we reason, our brains are capable of reason as well, right? So we reason that, wait a second, my brain's playing tricks on me. But the intuition of our brain, or the instinct of our brain, is to say that it always traveled in a straight line. Now, it's not going to look as odd as it might seem right now. The fish appears to be up above you, right? But what else appears to be up above you?
The seagrass.
Yeah, the grass that's in the water, the bottom of the pond, the water itself appears to be above you. So you're going to look up and you're going to see down in the pond. Does that make sense? So, I mean, think about this. Like, people are pretty much neutrally buoyant, right? Which means that in a situation like this, you look down, you see the bottom of the pond and the fish. You look up, you see the bottom of the pond and the fish. And you can imagine how easy it would be for, say, a diver to become disoriented underwater, right? Because you look down, you look up. Like, if you look straight up, you're going to see up, right? But if you look up at an angle, you're going to see the same thing as when you look down. Now, there is a solution for divers, right? How does a diver tell the difference between up and down? Usually not so much visually and not so much buoyantly, but bubbles. Yeah, bubbles. When you breathe out, the bubbles will always go up, right? Does that make sense? You had a question?
Yeah, so if just to make sure, if the angle of incidence is larger than the angle of refraction, like the purple line.
Okay, so in this case, this is happening right here. This happens when theta 1 is greater than theta c, the critical angle. This one happens when theta 1 is less than the critical angle. So when your angle of incidence is bigger than your critical angle, you will get reflection. Now, the reason I chose that purple ray is because it would have to be, if anything was going to be observed by this guy standing back here, it would have to be that purple ray that was refracting into his or her eyes. But as it turns out, that purple ray won't refract into his or her eyes because that purple ray ends up reflecting. The critical angle is beaten here. I got another one for you. What's this? This is a diamond, a perfectly shaped diamond. And that's important. The shape of a diamond is very important. Okay, guys, when you go to buy a diamond for somebody, don't do it soon, okay? Okay, like, wait a few years. Wait a bunch of years, actually. When you go to buy a diamond, there are 4 things that are really important with that diamond. And they may or may not explain this to you. It depends upon where you go. One of the things, they call them the 4 C's. One of the things is the color of the diamond. Okay, the color of the diamond. Generally, you want no color. But if it's a deep, nice color, then it makes it more valuable because they're so rare. You don't see colored diamonds very often, although it is possible. Okay? If it's just a little hint of yellow, like, you don't want that, right? If it's bright color, then we might want that as a diamond. So color is one of them. Okay? Usually no color. Okay? Another one is clarity. we want a clear diamond. Sometimes they're a little foggy. You don't want a foggy diamond, right? You want a clear diamond. So that's the second C. The third C is the carats. Carat relates to the size of the diamond. Obviously, the size of the diamond matters, right? The bigger it is, the more valuable it is. And finally, the fourth one is the cut of the diamond. So when I bought a diamond ring for my wife to be 20 years ago, the guy explained to me that the cut had to be just right, and otherwise the light wouldn't reflect properly within the diamond and whatever. And then after he was done his explanation, he said to me, he said, I forgot to ask you what you do. What do you do for a living? And I told him what I did. And the look on his face at first was like almost like a jaw drop, like, uh-oh, I hope I passed. But he did. Like, his explanation was perfect, and his explanation wasn't like any kind of made up stuff. It was a good explanation that really does show why diamonds that are cut properly sparkle so much. Now, the color, the clarity, I knew nothing about that before I bought a diamond ring. But the cut is pure physics. It has to be cut just right, and I'm going to explain why now. Here's a diamond, a cross-section of a diamond that's cut properly. You don't, like these numbers, percents, whatever, don't worry about that at all, okay? But this is cut properly. Any diamond should be cut at these angles. It doesn't matter whether it, from above, it's square or circle or oval, whatever. These are the angles that we want it cut at from the side. Because this promotes the most sparkling inside the diamond. And that's largely why we want diamonds, right? Is because they sparkle more than anything else, more than glass, more than cubic zirconium, whatever. When light enters the diamond, usually it enters from above, right? You got a ring on your hand, the light goes in from above, usually. Not always, but usually it's from above. Now, diamond has a very, very high index of refraction, 2.42 actually, index of refraction. That means that the critical angle for diamond is low. Okay, index is high, the critical angle is low, lower than it would be for glass or any other material. Which means if the critical angle is low, we have more or less chance of reflection taking place. More. It's easier to exceed a critical angle when you have a low critical angle, right? You're going to get more reflection taking place. Let's draw this out here, okay? Here's a ray of light coming in. Here's my normal line. Okay, this angle right here is not a particularly high angle, but because it's diamond, it may be exceeding the critical angle. And if it is, then that ray of light is going to reflect like this. If this was glass, let's say, then that ray of light striking at that angle might not exceed the critical angle, and it might end up doing this. If this is cut wrong, okay, then my angle may not be bigger than the critical angle, okay, and it refracts out instead of reflecting. Okay, but if this is diamond with such a high index refraction, therefore low critical angle, and it's cut right, then this ray of light exceeds the critical angle and it reflects. Guess what I see when it reflects? A sparkle. Right? I see a sparkle when the light reflects off of that diamond air boundary. Now it goes over to the other side here. We have another normal line drawn at 90 degrees here. This angle, not particularly big, but it's diamond. It's cut right. I'm exceeding the critical angle. What happens? It reflects. What do I see? What do I see? Another sparkle. Okay? And then the light comes back out the top, and I can see the light coming out the top. So we get multiple sparkles here. If the light came in and it was cut wrong and it refracted, or it was a lower index of refraction, which makes the critical angle higher, well, then you would see the boundary, because when light changes directions, you see a boundary. But you wouldn't see a sparkle. Maybe it reflects off of the first boundary, but then refracts out the second one if it's cut wrong. You see one sparkle. Well, rather see two sparkles, right? Two for the price of one. So it needs to be diamond with a high index, low critical angle, but it also needs to be cut properly. Does that make sense? One more that I'm going to draw here right now. that I don't have in the notes. The reason I'm going to draw this right now is because I thought of this the other day when somebody knocked on my door. And I don't know if you guys have had this or not. Somebody from TELUS knocked at my door the other day and said, we're putting fiber optic internet in Okotoks. They're spending $60 million, TELUS is, to put fiber optic cables all through Okotoks and hook up literally every house in Okotoks to fiber optic internet. So the guy knocks on my door and says, like, we need to just check out the entrance, the cable entrance to your house to see if it's capable of handling the wire coming from the street, okay, into your house. And if not, they actually have to dig a trench through the front yard. Turns out mine's not, so they have to dig a trench through my front yard. That's okay. Okay, I signed off on it in a heartbeat. Because fiber optic internet is way, way, way faster and offers way, way, way more capacity. And the reason it does that is because it doesn't use electrons moving through copper wire like the internet that I use now, right? I got wireless internet in my house, but ultimately, how does it get into my house? Electrons in a copper wire, right? Which severely limits the speed and the capacity of that internet signal. So, what it's going to be in several months is internet signals that are transmitted by light through glass wires, flexible glass wires. You got a beam of light that carries information, right? Like, think about this. Like when you turn on your radio, you hear information, right? The radio wave carries information. You hear voices. It carries information. When you turn on your cell phone and somebody sends you a text, okay, the light, the EMR, is carrying information. EMR can carry information. This is visible light, and it carries information, a lot of it. And that visible light, say carrying information, maybe strikes the boundary between the glass, which has, I'm going to say 1.50, although I don't know what the index refraction is of the glass that they use. Okay, it might be a little bit higher. The higher the better, right? Because the higher the index refraction, the lower the critical angle, and the easier it is to exceed it. If this angle right here is bigger than the critical angle, what happens to that ray? It reflects with very little signal loss. Like you always have signal loss in copper wire. We have very little, almost no signal loss at all right here. Strikes another boundary up here, what happens? Reflects, and so on, and so on, and so on. So it carries the information through this beam of light to the other end of the wire with no signal loss. Now, why is the capacity so much higher? Well, copper wire is a copper wire. A glass cable allows me to have another beam of light, which reflects, and so on, and so on. Does that make sense? So this is not, I'm not trying to advertise TELUS, per se. Okay, I don't know if Shaw has something similar or not, because I don't deal with Shaw, so I don't know if they have something similar or not. I really don't know. But the technology, the company aside, the technology, boy, it sure is something that we want in our houses. If we want fast upload and download speeds, and if we want high capacity, then the technology is definitely something we want. Okay, whether TELUS is the only one that offers it or not, I don't know. Okay, but I know that it's coming soon with them. Danielle, you had a question? Was your hand up a minute ago? Okay, sorry. That make sense? Okay, let's do an example here, and then I'm done with you for the day. Determine the critical angle for water. By the way, the index of refraction for water is, I believe, somebody just check this on your sheet, on your worksheet. I think it's 1.33. It is 1.33, yes. And of course, if we're talking about the critical angle for water, what's my other medium? Air, right? It's air. So we're going to say, we're going from air, by the way, has an index of refraction of 1.00. So which way am I going? Air to water or water to air? Do I know? Got to be water to air. Got to be water to air. So let's make this our water down here with an index of refraction of 1.33. This is our air up here with an index of refraction of 1.00. And let's say we're going this way. We're going from high to low index refraction. Now, I drew the water down below because, well, water doesn't usually sit above air, right? But it doesn't really matter. If you draw it the other way around, it's fine, as long as you have your light going from water to air. Now, if we want to find the critical angle, the angle at which reflection begins to occur, then we're looking at the situation where it skips along the boundary. What's theta 2? 90 degrees. So we're going to say sine theta c over, yeah, I'm just going to say nothing, because what's sine 90 always equal to? 1. Sine theta c equals n2 over n1. Now, watch what happens here. Okay, don't copy the rest down right away, because I'm going to make a mistake on purpose. Theta c is equal to the inverse sine of n2 over n1, which is the inverse sine of 1.33 over 1.00. Watch what happens when I do that. Remember, there's a mistake there, right? Watch what happens when I do this. I'm going to say theta is the inverse. Let's just check, see if I'm in degree mode first here. Yep. The inverse sine of 1.33 divided by 1. Look what happens. I get an error. Okay, what does that likely tell me I've done? Okay? Yeah, I've mixed up the indices of refraction, right? So let's fix it. Let's just fix it. Let's say it's, well, it makes sense. N2 over N1. This is the second medium. This is the first medium. It's going to be 1.00 over 1.33. Remember, you only get that error with critical angle problems, not with just regular Snell's law problems. Okay? That doesn't tell you whether you're right or wrong. Let's fix this up now. Let's say this time the inverse sine of 1 over 1.33 gives me 48.753, which rounded to, how many digits are we going to go to? I think on your data sheet it gives you air as 1.00, and on your worksheet it gives you water as 3 digits. I think it's 3 digits for both of them, which means we should round this to 3 digits, 48.8 degrees. Is that hard? Not particularly, I don't think. The good news is they're all pretty much the same. As a general rule of thumb, you know, like lots of times I give you the little, hey, if you remember this, you can kind of an indication that you're right or wrong, right? Like a range of something. Here's my little, you know, if you can remember this, it might be useful to you. The bigger the value of n is, the smaller the critical angle. So we got 48 degrees here. If we want to find the critical angle with, say, glass, it would be lower than 48. Diamond, even lower than 48. Why? Because those indices of refraction are bigger, yeah. Now, one final thing here. Usually one of the mediums is air, right? If they're not air, if it's like water and glass, or it would have to be glass and water, I guess. Diamond and water, diamond and glass. We're not so much looking at the index of refraction, we're looking at the difference in the index of refraction between the materials. If the difference in index is bigger, then the critical angle would be smaller. The bigger the difference in index, the smaller the critical angle. The bigger the difference in index, the smaller the critical angle. All right, let's take a look at the rest, please. The rest of worksheet number 17. And I'm also going to post practice question set number 22 here.